Okay, so we're going to cover some things related to Boolean logic and set algebra. And this is a continuation of yesterday, but we're going to be a little quick about it. Quicker than maybe it deserves, but as I said a few moments ago, this won't apply as much to the technical interview or to kind of your first parts of the DSI. Now, just because that's the case doesn't mean it's not important, and I want to be very clear about that. There are a number of very intuitive laws in Boolean logic or set algebra. Some of these we've already touched on, like the commutative and associative properties. But then there are a number of other fairly interesting logical constructs that I'm going to do my best to fly through. It's okay if you don't absorb all of this as we go. And there are a couple things I might even skip, although when I'm looking at this, if I skip anything, I should skip all of it. And I was honestly debating maybe we skip this lecture and go into basic probability directly. Still, I think exposure to this is good. And for that reason, I'm going to stick with this for at least this round, and I'm going to reconsider it for the next round of premium prep, if that makes sense. So I think y'all will be the deciding factor in that. Okay, so we've got these different laws, and like I said, these are related to logic, and they're related to set algebra. Now, what do I mean by logic and set algebra? Well, I'm going to create a sort of parallel concept where we're equating set algebra with Boolean logic. Now, we talked sets, and I think the way that I like to consider this is that, okay, well, let's say we have a Boolean like true. True represents something. Okay, it represents something kind of in the in the universe, some other phenomenon that has a set of outcomes. So in some ways, true is indicative of it's a qualification on some set of items. So maybe we've got 2, 4, 12, and 16. And the question that we are considering here is, are all items even, right? And if that's the case, well, the answer is true, okay? And then if we have some other set, right, if we've got some other set of items that's like, 3, 4, 12, and 18, well, that's obviously false. If the question is, are these all even, right? Now, what if we change the question? If we change the question to be something a little bit different and we ask, are any even? We could ask that question, and in that case, well, this isn't false anymore, this second one. This would be true. So we can think about a Boolean as being a descriptor on some phenomenon. And in this case, I'm, the phenomenon I'm stating is like, well, it's a descriptor of whether or not there are any even values in, some set of numbers. And so we can apply this rule against a bunch of different things and get trues and falses, depending on whether or not we break or whether we follow that rule or not, right? So here's 3, 9, 11. Well, that would obviously be false under this this condition, okay? So if you just trust, at least for now, we could build out more theoretical foundation here, but I'm just going to ask you to trust that all the laws that we're going to look at will apply to both sets and to Boolean operations. That's really what I'm trying to say here, is that we're going to equate these two spaces, and we can actually do that through the rigor of logic and through and by the same way that we have the rigor of set algebra. Okay. Now, this is something I mentioned before, but we want to be pretty clear about it. We're going to make these we're going to equate these concepts. we're going to equate union with or. We're going to equate intersection with and, okay? And we're going to equate complement with not. And I think I'll demonstrate this with our first law, which is commutative, the commutative law. Okay? So what do we mean by this? Well, if we have the union of A with B, that is going to be the same thing as the union of B with A. That just makes sense, right? That just makes sense. Like this with this, and we're talking about all of this, well, it's the same way no matter how we arrange that. It's not really too much of a concern. And by the same reasoning, the intersection of A with B is the same as the intersection of B with A. Now, that's easy enough to see with sets. We could also say true or true is the same thing as true or true. That's not the best. It might make more sense to say true or false is going to be the same thing as false or true, right? Those are obviously equivalent. We could also say true and false is going to be equivalent with false and true. All of those things make sense, and all of those are examples of something being commutative. So I'll demonstrate this one in code just to, concretize it. And let's say we have two sets. We have A, B, and C. And this code is in the notes as well, but I just want to talk through it. And then we have set 2, which is going to be C, D, and E. So C, D, and E. And so we've got that. If we want to consider A union B being equal to B union A way that we can do that, since we are now actually, notice we are now actually dealing with sets. These are sets, and maybe I can just demonstrate that. Print type of set 1. These are no longer lists, just to be very clear. So axioms of probability. Notice this is class set, not class list. We're just using curly braces right here. So now that we have sets, now that we're using sets, we actually have set operations built in. We have methods associated with the set object, and that's going to be really convenient. So what I can do here is say set1.union of set 2, right? And I'm going to ask the question, is that the same as set2.union of set 1? And I think what we'll find out is, yeah, of course, those are the same thing. I can change this out for set intersect, and in this case, can I do that? I can. Okay, so I'll just do intersection. So set 1 intersection with set 2, is that the same as set 2 intersection with set 1? And it shouldn't be too surprising that it is. Now we can take this a little bit further. We can say A is true, B is false, and I'm going to work out of this idea a lot. A being true, B being false, and C being true. But of course we could change those values depending on what we're doing. So A is true, B is false. Is A or B, is that equal to B or A? And I think this is much easier to see. Like if I print that, I think we're going to see that that is true. And then I can swap this or for ands, and we should see that all of these ideas are true. So I'm not going to do this with every law. I'm going to do it for some laws, and other ones, if you want to see a code justification for that, definitely look in the slides. But I think this is going to be pretty intuitive. Some of these will be very intuitive, and a lot of these I'm going to do on paper, or digital paper. Okay, so that's the commutative law. Now we have the associative law. And this one is pretty straightforward. Let's say we have A, B, and C, and we're going to union them. it doesn't matter if we union A with B first, or if we union B with C first. That does not matter. Okay? I think that makes sense, right? It shouldn't be surprising, especially after everything we did yesterday. The same is going to apply for A, B, C, where we union A with B first, as opposed to unioning B with C. Intersect. If we intersect A with B first, as opposed to intersecting B with C first. These will evaluate in the same way. Doesn't really matter which way we do that first. So those are the associative and the commutative and associative laws. This one, the distributive law, is maybe not as obvious, and we can demonstrate this. But this is one of those ones that does really come in handy in the world of logic, and you'll be surprised when it comes in handy. Not right away, but further down the road, maybe in the second half of the DSI, some of these will come back around to help or haunt you depending on what's going on. So in this case, I'm going to union A with the intersection of B and C, okay? Now, this is going to extrapolate out in very much the same way that we see the distributive property for just, like for multiplication extrapolate out when we have multiplication associated with addition. And there is kind of this association, right? Intersection kind of feels in some way like multiplication in some way. And union feels sort of like addition in some way. But before we jump down the philosophical hole of that, let's just think about what this would extrapolate out to. This is actually going to be the set A unioned with B, and then that is going to be intersected. I can draw an intersection here, but the intersection is applied through the idea of multiplication, as I said. This is going to be the same as A union B intersected with A union C. Okay? So that's one form of the distributive property here. And the other form would be A intersected with B union C. That's going to be the same idea, or that's going to be the same result as A intersected with B, right? We're doing this again. We're taking this through. A intersect with B, and that's going to be unioned with A intersected with C. So we can demonstrate this. I think this one's nice to demonstrate, actually, because it's maybe a little bit baffling, but we can work with it. So here we've got set 1 and set 2. And I'm just going to do set 2 intersection with set 3. And let's see, let's do, let me do this. A intersect, what would be the best way to do this? Yeah, set 2 intersection with set 3. I need a set 3. I need to have some shared items. Let's do B, let's do F, and D. We'll do that. How about that? BFD. Okay. So if we're thinking about this, snag all of this. Okay. All right, so let's think of set 1 as being A, set 2 being B, and set 3 being C, okay? And we can say, well, A dot union with B dot intersection with C, right? So that's an expression that follows what we're seeing up here, this A union B intersection C. So the intersection with C is going to happen first, and we should be able to see what that is. So the question is this equivalent to, we've got A intersection with B, and that will be unioned. Oh my gosh, these code suggestions are just popping up all over the place. So I'm sorry, A union B is what that should be. So we've got that, the result of that intersected with A union C. Okay, if you see an error in here, please let me know. And let's see if that evaluates to true. Are those indeed the same things? Well, they aren't if there's a syntax error. So, is that it? That looks like it. Okay. And those are indeed the same thing. Okay? So, this distributive property is kind of cool. Now, are we going to think about it in sets? Probably not so much. We're probably going to think about this more in terms of logic. And for the logic here, I'm going to do A is true. Like I said, B is false, and C is true. And I'm going to try to stick to this just so that we're all, kind of dealing with the same Booleans. But in this case, I can say A or B and C, right? This is a much easier way to see it than with all that union and intersection method that I did above. Is this the same as A or B and A or C, right? And I'll just wrap all of that in parentheses, so there's no potential for confusion around what's happening here. Okay, so are these equivalent? They are. That evaluates to true. That this is an equivalent operation to this. Okay. So let's think about some. So that's our three sort of basic laws. We're going to think about a number of other laws now, and we're going to fly through these. Some of these are going to be a little bit obvious. Okay, they're going to be what we might think of as tautologies, and I'll point these out when they're really obvious. And I'm not going to demonstrate them with code. It wouldn't make it would. There is code that I could demonstrate them with, but I think it's easy enough to say, well, okay, what if we union A with A? What is that going to be? What do you think? Just put in the Slack. What do you think that's going to be? Yeah, it's just going to be A, right? And I think that, I don't want to say, oh, that should be obvious or something like that, but it makes sense if you think about it. You take something and you union it with itself. It's going to be itself. And that's, not too mystical. I think it's pretty accessible. Yeah, exactly. A union A is A union A is A union A, etc. Same goes for the intersection, right? A intersect A, and we can think about that even, oh, here's A, and here's A, right? The Venn diagram of it is just on itself, so it is itself. So I think that's pretty easy to conceptualize. We call those laws idempotent laws. Do you need to remember that? No, but it's a word and it exists. So that's the word that we use to describe that. Now, there are a couple other kind of tautology type laws. One is domination law, or there's two laws here actually. One of them is going to be intersection with the universal set, okay? And one of them is going to be intersection with the null set. Now, what do I mean by universal set? The universal set is everything, right? This is everything that we are considering, that's our universal set. So, right, we think about that as everything. That's we've been calling that S. We could call it U. Either way, it's what we're dealing with. And then we've got this idea, the null set or the empty set, and this is nothing. There is nothing in there. There are no objects in there. So this maybe goes without saying, but the intersection of A with everything is going to be A. And the intersection of A with nothing is going to be nothing. So just kind of tautology, pretty straightforward on that one. Now, I think here's where it gets more interesting. We have ideas of absorption. And this is where logic gets pretty fun. It becomes kind of a game. Like, can you take something that's more complex and make it simpler? Or obviously you can take something that's more simple and make it more complex. But we can extrapolate and simplify logic through things like absorption laws. So here's one of them. A is, let's say A union A intersect B. So this is going to equal A. Now, look at this. We're going from this more complex thing to simply A. We're absorbing everything into A. Okay, so let's define A, B, and C, and let's just, let's define A and B initially, and we won't worry about C quite yet. So if A is true and B is false, and then we'll leave C out for this one because we don't have a C. So what we can say is, well, let's equate this to A or A and B. And we can break this down. We can simplify this. So let's insert true for A. Let's insert true for A here. And we'll insert false for B. True and false, well, that's false. True or false, that is true. We can see that we've absorbed A union A intersect B into A, and it's just true. Now, the other absorption law here is going to be A intersect A union B. That's going to equal A. And again, we'll do A is true, B is false, and we'll just think about, okay, well, A and A or B, right? So, and I'm just going to simplify this to single letters. I'm not going to write out true. I'll just say true and true or false. Well, true or false, what is that? That's true. True and true, what is that? That's true. We've absorbed into A. So let's think about a couple more of these laws. There's a few of them, and they're kind of fun. Sorry, I kind of skipped over this one. It's out of order on our slides. This should really be in kind of those tautology laws. The identity property, if we union A with nothing, we get A, right? Just makes sense. Okay, so let's take that a little bit further. Oh gosh, there's a few of these. Not null set is the universal set. Not universal set is the null set. Makes sense. So that's another one of those tautologies. I'm just going to scroll down to make sure. Oh, there's more. Okay. This is obvious, but it's also important to say it. We have this idea of involution, or double negatives, essentially is what this is. If we have not A, well, that's just A, right? If we have not A, it's A. Pretty easy in that one. Okay. So here's one of the most useful laws, and it's not named as far as I know. I'm sure somebody somewhere has named it, but when I was studying circuit design, I would use this all the time to simplify circuits, and it actually turns out to be very, very helpful. So if you have, I'll just call this unnamed, and we'll say A is true and B is false again. So the idea here is A intersect B. If we union that with A, and I'm going to do an overbar here for not, okay? A not B, okay? A intersect not B is what that means. If we do that, this actually works out. Well, let's just plug in values and see what happens. So this is true and false, or, and I'll put parens just to delineate this clearly, or true and not false. Okay, let's work through this bit by bit. True and false, well, that evaluates to false, right? True and false evaluates to false. Not false, well, that evaluates to true. True and true, that evaluates to true. False or true evaluates to true. So this complex statement actually boils down to it's sort of like an absorption law, but we don't consider it to be an absorption law exactly. But essentially, it's doing a similar thing to what the absorption laws do. Okay, so we just flew through most of the logical laws, and now we're going to sit and focus on the ones that people ask about the most, okay? And they ask about them because they're very helpful. There are two laws that we refer to as De Morgan's laws. Where might somebody ask you about these? Maybe in an interview, possibly. Not in our technical interview, we're not going to ask you about them there, but maybe in a job interview. Maybe in, if you are going to be in a SQL heavy position, you might need to answer a lot of these kinds of logic simplification problems. That's not out of the realm of possibilities. So law 1 here is if we have A unioned with B, okay, and we say not to that whole thing. So not A union B, okay? Notice we can't do much with this. We potentially can't do much with this in its present form. But here's an amazing thing. This is equivalent to not A intersected with not B, okay? In some sense, we break A and B out of this cage, potentially. And let me demonstrate this. We'll do A is true, B is false. And we'll work through this. We'll work through it on both sides. So this is going to be, true or false, and not to that whole thing. And then we've got not true and not false. Okay, well, let's work through these. Not true, well, that's false. And not false is true. Okay, so that works out to false and true. Well, that's false. Let's work through this. So true or false within here is going to be true. So true, right? We get not true, which is false. And we can see that those are equivalent. So that's one of De Morgan's laws, this law up here. Let's consider De Morgan's 2. So De Morgan's 2 is not intersection AB, that's going to be equivalent to not A union not B. Okay. Again, A is true, B is false. Let's just plug these in, and we'll say this is true and false, throwing not over that. And then we've got not true or not false. Okay, so let's work through this. Not true is false, or not false is true. So false or true, that evaluates to true. And here we've got true and false. Well, that's false, right? Not false is true, and we can see that those are equivalent. Okay. Again, these laws are really helpful for logic. They're helpful for circuit reduction, which is something you might end up doing in network design, in like neural net design. There might be ways that you were trying to simplify the logic in your network. That might happen depending on what space you're in. Really, in the future, you're going to want to know at least De Morgan's, right? You want to know at least De Morgan's. The other ones, aside from the obvious ones, the sort of tautological ones, do you really need to know, do you need to know, let's say, the that strange absorption kind of law, the unnamed absorption law? Probably not. Not unless you're dealing with it every day. Okay. So I'm going to show you something that is kind of from some of these ideas. We can diagram logic, okay? And that can look a number of different ways. So let's say we have the AND operation. The way that we might draw the AND operation would be like this. We have two inputs that we see here, right? We've got an input there and an input there, and we've got an output there, okay? We call that an AND gate. We also have OR gates, okay? So an OR gate looks like this. Same thing. This is just an OR operation, two inputs, and we have an output. We have, the only other gate that I want to show you here is what we call the NOT gate, okay? There are a number of other gates. Under the hood, your computer uses NAND gates, but let's not worry about that. There's XOR operations, which are really cool, but let's set that aside actually too. So with NOT, let's say we have one input and we have one output, okay? What does this triangle mean? Not a whole lot, okay? What this really means is we perform an operation in some moment, right? Like let's say we have an and then the result of that and, we make it a NOT, okay? And that's actually a NAND gate. But when we're looking at this little symbol right here, what that is its negation of the output of that gate, okay? So we've got these three gates. With this, we can map something out. And I'll put these up here as reference. And let's make some, let's make some gates, Let's have some inputs. I'm going to have A, B, and we're going to put that into an AND gate. And the output of that is going to go into an OR gate. And there's going to be another input here that is C. And let's do A and C into an OR gate here. okay? And let's not that operation. And let's put all of that into, let's do an OR gate. Let's do an OR gate there, and then not that operation for a single output. Okay, so A is true, B is false, C is true. We can work through this, okay? We can actually plug these values in. And so this is going to be true, false, true, true, true. And we can process this. So true and false gets processed as false, right? So the input over here is going to be false. But false or true, well, false or true, that is going to evaluate to be true. And so we can see we've got one input here to our NOR gate. That's a not OR gate. And we just need to figure out what's happening over here. So true or true, well, that's true, but then we have a not here, right? So that becomes false. True or false will evaluate to true, but then we've got a not here, and we're going to ultimately evaluate that to be false, right? True or false would be true, but we apply not and we get false. So you might have a question looking at this: can we make this a simpler circuit? Well, it's very possible. One of the ways that we could do that is we could try all different possible values of trues and falses for A, B, and C. And then we can look at all the potential results of that. That's something we could do. That's not what we're going to do. And I'm not going to simplify this, but I want to put this food for thought there. It's that maybe this circuit is actually overcomplicated. And I might be performing all these logical operations when maybe I only need 2 gates to do the same thing. That's not uncommon. And when you're programming, you might have a lot of complex logic in certain statements that can actually be expressed in somewhat simpler logic. Not all the time, but but it is something to keep in mind. Okay, so hopefully these logical operations are at least interesting. Okay, at least interesting. They will come in handy when you learn them more deeply, like in the DSI and after the DSI. You'll find applications for these kinds of things. For now, set it aside. Remember that it's there, but don't worry too much about it. We won't test you on that for the technical interview, and you're not going to hit anything on that in the first couple weeks of the DSI. Okay, so let's move to the next step of things. We're going to compute basic probabilities. And so we're sort of starting to leave set theory behind. Although what we're not leaving behind is this idea of the probability of A being the cardinality of A over the cardinality of S, where S is the sample space that contains A. Now, how might we think about this? Just to be very clear, let's say S is composed of, A, B, C, D, E, F. And let's say A is composed of C, E, and F. The probability of A is going to be the cardinality, or kind of like the magnitude of A, which is going to be 3, over the cardinality or magnitude of S, which is 1, 2, 3, 4, 5, 6. The probability of event A occurring in this idea is 0.5, or 3 out of 6, right? So, this foundation is pretty straightforward. I think it's pretty easy, and but there are complexities in how we start approaching figuring this stuff out, and that's where we're going to put a lot of focus. So there are a couple of these, a couple examples in here, but I covered those examples yesterday. So what I'm going to do instead is skip those. I'm going to just talk a little bit of notation. Now you noticed I wrote this word prob, right? Probability of A. That's common. What I'm going to do in general, and the way that I pretty much always notate this, I'm going to say P of A. P of A is going to be probability of A. So that's all that means. We could also ask, well, the probability of not A, right? In the case that we just saw, that would again be 0.5, right? It's still 3 out of 6 items. We can ask something like, what is the probability of A intersect B? We can ask, what is the probability of A A union B? Oh. We can ask that question. Here's something a little new. We can ask the probability of A given B. Okay? We're going to have pretty much a whole lecture on this idea, probability of A given B. That's a conditional probability. That's how we think about that. And that's going to be our main pen and paper day, is going to be talking about pretty much this idea the whole time. Okay, so we already broached this idea of building a sample space through counting. Counting is going to be our other foundational concept of probability. Set theory is a foundational concept of probability. Counting is our other foundational concept. So let's count something. And let's think of this. I'm going to use the example that's on this slide because it's a little bit, it's a little magical, okay? And what I mean by magical is like, we're not going to think numerically in this counting, ironically, right? Let's say we have a set of pets. And what we have is a cat, which I'm going to represent with a C. We have a dog, I'm going to represent with a D. We have a ferret, which I'm going to represent with an F. And we have a goldfish, which I'm going to represent with a G. So this is our set of pets. How do we count using pets? All right. So imagine we have a room, and these 4 pets are in that room. And we perfectly randomly can go into the room with our eyes closed and pick a pet and look at it, and it's going to be a cat, a dog, a goldfish, or a ferret. We put it back, leave the room, come back in, and do that again, okay? And we're going to get a cat, a dog, or a ferret, or a goldfish with equal probability. The prior grabbing of a pet does not affect the subsequent grabbing of a pet. We call this concept with replacement. When we pick a pet, we're not taking it away from the pool of choices. You can also think about this as an infinite room, like a room with infinite pets in it. Equal partitions of cats, dogs, ferrets, and goldfish. There's no difference in the probability of selecting any one of them. And if you select one, it doesn't affect the next selection. So how do we count these? Well, if we're talking about drawing 4 pets, one of the possibilities is we get a cat, then we get a cat, we get a cat, and then we get a cat, right? And it may not be obvious, this is a number with 4 places, okay? And then here's another possibility. We get a cat, and then a cat, and then a cat, and then a dog. And then a cat, 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 and a ferret, cat, 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 goldfish. And now let's think of another possibility. What about cat, cat, and then dog, and then a cat? Then cat, cat, dog, and then a dog. Cat, cat, dog, and then a ferret, cat, cat, dog, and a goldfish. Okay? Now, you might be noticing the pattern here. This is just like counting, except we're counting in a base 4 system. Okay? What makes it base 4? Well, there's 4 items. There's 4 elements here. This is a base 4 system. We're used to counting in a base 10 system. When we count in base 10, we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we roll the 9 over to 0, and we add 1 to the left. And if you think about it, that's all I'm doing here, but with base 4. I'm going cat, dog, ferret, goldfish, cat, dog, ferret, goldfish. That far right position is rolling over. And, sorry, the second to the right position is rolling over when we get to our last element here, which is goldfish. We get to goldfish, and then this C rolls over to a D. And we can see that clearly. Now, how do we do this with Python? It turns out it's pretty easy to do this with Python. So I'll just demonstrate. So we have some pets, and we have a cat, a dog, a ferret, and a goldfish. And I'm going to use these single letters because I think they're easier to see in the output. Let's consider in an exhaustive way, all the potential outcomes. So pet outcomes. I'm going to say for pet 1 in pets, and then pet 2, pet 3, pet 4. And we've got pet 2, pet 3, and pet 4. Okay, so pet outcomes. With this, we can append pet 1, pet 2, pet 3, and pet 4. Okay, well, now, so that actually constructs our sample space of possible 4 selections with replacement. That's what that does for us. So we can say for pet outcome, in pet outcomes, let's just print each pet outcome. And what we're going to see, we're going to see a counting system that is composed of, C, D, F, G. So Python, basic probability, and that's what we get. So offhand, how many items, if somebody has a thought on this, how many potential outcomes are there in our set of outcomes? How many total, right? From CCCC all the way down to GGGG. How many do you think are there? So yeah, and how do you calculate this? Like, how do you think about calculating it? Got 4 places of 4 items. There's 2 ways we can think about this. Exactly, it's 4 to the 4th power. Yeah, and let's just verify that. So print 4 to the 4th power, and let's print the length of our pet outcomes. And these should be the same number. 256. Okay, it's pretty straightforward, right? That's how we, this is a way to count. And I'm not saying, how do I say this? I'm not saying you should spend a lot of time making nested for loops in your life. The less you can nest for loops, the better. However, if you're doing like pure counting, this is kind of the way to do it. It's not the only way. Let me take that back. It is the only way. You can just make it look nicer. But yeah, this is just simply counting. And each one of these is the place where pet 4 is the furthest place to the right. We can do this with just about anything, actually. And we can start asking questions in terms of our pets. Like what is the probability? This is a breakout, but I'm not going to ask it as a breakout. I just want to show you this because we're going to do a lot of this kind of thing. What is the probability that a person will select 2 or more cats when randomly choosing 4 pets with replacement? Okay. Well, we can calculate this. This is something that we if we take this counting approach, we can figure out 2 or more pets easily with Python. So let me show you how you do that. I'm going to call this 2 or more cats. I'm going to make that an empty list. I could just call this S. Sorry, I could just call this A, but I'll call it 2 or more cats. And for pet outcome in pet outcomes, if pet outcome dot count of C is greater than or equal to 2, right? 2 or more cats. Then 2 or more cats, we can append that outcome, okay? And we can look at this, we can look at these outcomes, right? All the different ways that we can get 2 or more cats. And let's just take a peek at that. So here's kind of a wall of lists. We can get all cats, we can get 3 cats and a dog, we can get 3 cats and a ferret. We can get a ferret, a cat, a ferret, and a cat, right? There's just a bunch of different ways that we might get 2 or more cats. Turns out those are different permutations of these animals, but we'll cover permutations and combinations with some depth in a couple days. Now, how do we calculate the probability that a person will select 2 or more cats? Well, that's easy enough to do. We can say the cardinality of A, right? So the cardinality of A, that's just the length of our 2 or more cats. And the cardinality of S is just the length of our pet outcomes. So the probability of 2 or more cats, this isn't a great name. I'm not trying to encourage you to use this kind of naming convention exactly. It's not too bad, but just trying to illustrate this in plain language. It's just the cardinality of A over the cardinality of S, which we can represent, or we can just print out once we have it, right? So what is that? 0.261, basically 0.2612. So there is a 26.2% chance that we're going to get 2 or more cats if we select, randomly. You could use a little bit of you could be critical about this, and you could say, oh, well, I think that this is going to be the same as getting 2 or more dogs, or 2 or more ferrets, or 2 or more goldfish, and you wouldn't be wrong, right? Those are going to be the same probability. The occurrence of cats across this numbering system is the volume of the occurrence of cats across this numbering system is the same as the volume of ferrets across this numbering system. So kind of under the hood, the logic of probability is not too bad. I think it's pretty straightforward, and we can see that. So I'm going to comment out everything that's printing, and we'll focus on a quick breakout that extends this idea. So I'm going to put this up here. I'm going to share a function with you called coin flip, and you're going to use this function. So what we were just doing, right, that was counting. But what you're going to do now is sampling. And we're going to spend time talking about counting versus sampling and everything like that. But for now, we're just going to touch on this subject and utilize it. So write a function called series of flips. And series of flips will have one parameter, n, n represents the number of coin flips. And you're going to return a list of length n containing n random coin flips. So I provided you a function that does a single coin flip. You're going to return a list that contains the results of n coin flips. So I'm going to put 5 minutes on the timer. And yeah, try to code that function. Series of flips. Okay, so I'm going to go ahead and code this out. Let's see if I can resize that. So we're going to call this series of flips. Okay, def series of flips. It has one parameter, which is going to be the number of coin flips. Okay, we're going to return a list of length n. So I'm assuming we're collecting into that list, and I'm going to return that list. Maybe I'll just call this flips. Why not? And so we're going to do something n times. We're going to call out to coin flip n times. So this is going to be for whatever in range n. Now, why did I say whatever? I'm going to use the underscore because we don't need that number. We're just going to throw it away. It's not important. So for whatever in range n, we're going to conduct a coin flip, and we don't pass anything into that. We're just going to say flips.append the coin flip. We return flips, and that is that function. So I do need to copy in the coin flip function from the notes. Just put that in there. And if we perform this series of flips, and let's do 10 coin flips, we'll see that we get a series of coin flips, right? Tails, tails, heads, tails, heads, tails, heads, tails, tails, tails. If I just flip this 4 times, we'll see that, right? Heads, tails, heads, heads. So either way, that seems to work. So I'll paste that into Slack so that everyone has it. And let me see if we should take a break now. Yeah, let's take a break now. Let's take a 5-minute break, and when we come back, we're going to use this function to take a sampling approach to estimating a probability. So I'll put 5 minutes on here, and I'll see y'all back here shortly. Okay, so we're going to get back into it with a breakout. The breakout is going to be sort of a filtering process based on this series of flips function. Okay, so let me go ahead and give you. Oh, whoops. Give you something to work with here. So here's the kind of the definition of the breakout. You're going to write a function called forFlip sample space, and it takes no arguments. It should return a list of all possible outcomes for coin flips, right? Heads, 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 tails, heads, heads, tails, heads, 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 tails, tails, and so on. Oh my gosh, are we really going to do that? I think I may have already coded something to that effect. You know what? Let me see where this is going. No, let's do this. Let's do this. Let's do this in a moment. Sorry. Let's consider this series of flips function. And let me talk about this for just a second more. So I want to point out to you that this is different from counting, right? What this is doing is sampling, okay? We're sampling a series of coin flips. So in this case, we were counting. We were making an exhaustive list of things. Now, if we're sampling, right, we can think about sampling in terms of counting to some degree, right? Where we construct some exhaustive list of outcomes, right? So, you know, heads, 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 tails, all the way down to, you know, tails, 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 heads, and tails, 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 right? We can think about this as being out there in the universe. And if we are, constructing, if we're sampling from this and we're trying to sample every four flip combination, every four flip permutation is what that would be, then we're going to draw something randomly out of this. And maybe it's going to be, you know, heads, heads, tails, heads. And we draw something else out of it, and maybe that's going to be, you know, heads, 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 tails, and draw something else out, and maybe it's tails, 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 heads, and so on. But if we do this enough, right? If we do this, like, say, let's say we do this 1,000 times, this process of drawing things out. If we do this a whole lot of times, then the frequency of occurrence of certain items will start to match the frequency of occurrence of the items in our actual theoretical counting space, the exhaustive counting space. It will occur with the same frequency. These ratios will start to balance out. And all of these outcomes are equally likely, but what if we have a rule that's like, well, let's think about this as the count of heads. So this count of heads would be 3, and this count of heads would also be 3. This count of heads would be 1, okay? So if we're starting to think about the frequency of these occurrences like this, we can take a sampling approach, or we can take a counting approach. And ultimately, if we sample enough times, then our frequencies of occurrences of these counts, even though there's two different ways to get 3, so 3 is going to be more likely than, say, 1, right? I'm sorry, that's not true. The most likely outcome would actually be 2. So let's say we had something like heads, heads, tails, tails, and then tails, heads, tails, heads. Those would both be 2. But anyway, at any rate, the frequency of these occurrences is going to start matching the frequency of the occurrences in the counting approach. And that's important to consider. We're going to spend some time on that concept later. So that's that's why I'm demonstrating this idea that we can sample. Sampling is a very powerful tool for us, and it can solve problems where counting isn't going to work for us. So now, with that said, I'm going to have you write a function where you're not sampling, but you are building a sample space, right? And through building a sample space, you're going to build that sample space through counting, essentially, okay? So for flip sample space takes no arguments. It should return a list of all possible outcomes for 4 coin flips. And I'm going to put 5 minutes down for this, not 4. So go ahead and get started. If you have any questions, post them in the Slack about how to do this. Oh, so I was going to do 5, and I am. Okay, so this is very much like that four animals, cat, dog, goldfish, ferret problem. So this is, we can construct this pretty easy. Def for, I'll make this a little bit bigger, for flip sample space, and we can say that our flips are composed of heads and tails, right? Heads and tails. And we've got, we'll do that, flips. And then, we've got our list of outcomes. Okay, so for F1 in flips, and then we can do F2, F3, F4, and F2, F3, F4. And I can do outcomes dot append. That's going to be F1, F2, F3, and F4. So that actually, that's all we need to do to construct those outcomes. So there we go. And I'm going to call out to this. I'm going to say outcomes gets for flip sample space. And then I can iterate through this like so. For outcome in outcomes, we can print the outcome. So I'll go ahead and run this. I'll paste it in first, and then I'll run it. Oh, takes exactly one argument. 4 were given. Oh, well, that makes sense. That should be a list. Sorry about that. Should have run it first. Let me fix that in the Slack as well. Okay. So when we look at this, this is just counting. And notice that the far right column of this is just going heads, tails, heads, tails, heads, tails. And then it's going heads, heads, tails, tails, heads, heads, tails, tails. Then it's going heads, 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 tails, 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 tails. And then heads, heads, heads 8 times and tails 8 times as well. This has 2 to the 4 power outcomes, right? 2 times 2 times 2 times 2. And we can see that with our nested for loop. That's exactly the same thing as what's happening there. So I just want to point this out in terms of how counting works. Of course, we're flipping every time here. And then once we exhaust the possibilities for here, so heads, tails, well, then we have to flip back to heads, right? When we do that, we flip here, right? Flip here, we flip here, and so on. And that same property is going to apply down the line of these. And in fact, that'll apply to any numeric system that we're going to deal with. So turns out this is binary. There's 2 items, and they're happening in this, and they're occurring in this way. This is literally counting in binary. We could replace these values with 0s and 1s, and we would see that clearly. We're going to get kind of deeper into binary at some point very soon. But for now, I'm just pointing out that is binary, and that's what we would call a base 2 system, right? Because there's 2 potential elements. Okay, so you're going to use that function, okay, in the next breakout. So you're going to reference that 4 flip sample space. And it should be corrected. I fixed what was going wrong there. And you're going to write some code that looks through those outcomes, okay? And delivers, oh, you know what? Let me give you a little bit more to work with. Give you these as well. So you're going to want to call the function. Then you're going to want to traverse the function. So I just want to give you that as well. So we're going to do 4 minutes on this. You're going to traverse those outcomes, and you're going to collect into A. You define some A, and collect into that any values, any outcomes that have exactly 3 heads in them. Right? Here are different possibilities: heads, 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 tails, heads, heads, tails, heads, heads, tails, tails, heads, heads, tails, heads, heads, heads. So you want to collect those, right? And then you want to look at the cardinality of 3 heads, which should be 4, but you want to do this procedurally, right? And divide that by the cardinality of the outcomes. So go ahead and do that, and I'm putting 4 minutes on the timer. Okay, so what I'm going to walk you through is essentially it's a thing that you'll need to be able to do, right? You need to be able to create a sample space, and you need to be able to go through that sample space and filter out the subset of interest. And then we can ask a question, well, what is the probability of getting one of those outcomes? And we'll see that here. So in this case, we're considering the probability in 4 coin flips getting, I'll just do it like this. What is the probability that in 4 coin flips you get exactly 3 heads? Well, let's create our subset A. And I'm just going to do a list of lists for each outcome in outcomes. If the outcome.count of h's is exactly 4. Sorry, is exactly 3. Then we can say a.append. We can append that outcome. And our probability is simply going to be the length of A divided by the length of the outcomes, right? Outcomes is a stand-in here for S. So the probability that in 4 coin flips you get exactly 3 heads is going to be 0.25. Now, can we verify that somehow? Well, we could scroll up and get a sense of this, looking at this. So here's 1, here's 2, 3. There's got to be a 4th one in there somewhere, right? So 1, 2, right? 3, and 4. So we can see that there's 4 possibilities, and we can divide that by the number of items, which is 16, which is just 2 to the 4th. Okay, so this kind of question, it's going to be really important to be able to answer this kind of question. Let's think about a special case of this where maybe you won't need to use counting, okay? And this is kind of a lead-in to basic probability, actually. So let's think of 10 coin flips. So 10 coin flips. What is the probability of getting all heads? How would we do that? Would we do that with 10 nested for loops? You know, we could try, right? We could build that sample space. It would be a lot like this. You know, I could just quickly try to adapt this and see what happens. But I just want to point something out, that this is going to be not only sort of really terrible looking code, there's a much easier, better way to do this. So F5, F6, F7, F8, F9, F10. Okay, well, let's do that. Let's just see what happens, you know. F5, F6, F7, F8, F9, F10. Yeah, and, you know, I hope you're thinking about the possible ways, a possibly different way to calculate getting all heads in this approach, right? Instead of building a 10 flip sample space like so. So, you know, for outcome in 10 flip sample space, let's print the outcome, and let's just run that. Okay, this is pretty massive, you know, and it's going to take me a while to scroll up. Well, not that long actually, but it took me a little bit of time to scroll up. But there's only one outcome here. There's only one outcome here that has all heads. And so if there's only one outcome that has all heads, then we can think about this a little differently. We can say, well, an easier way to approach this is to say there's only one outcome. So it's 1 out of how many possible outcomes? Well, it turns out it's 1 out of 2 to the 10th outcomes. And that looks like 0.000976 or 977 to round up. So how do we want to think about this? We can think about this in a different way. We can say that this is actually, well, heads, getting that the first time, there's a 0.5 probability. Getting heads the second time is another 0.5 probability, and we can actually just multiply those two together and see that that's 0.25. Now, if we were to count that, it would be, tails, 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 heads, 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 tails, heads, heads. Oops. Heads, heads. And we can see that 1 out of 4, or 0.25, is the frequency of occurrence of that. We could tack more values onto this, and what we would continue to see, is that we could just, in fact, keep doing this, right? 0.5 times 0.5 times 0.5 times 0.5, and so on. So this is a specific permutation, right? If we have 10 of these, this is a specific permutation of flips. There's 10 of them. And this is going to be 0.5 to the 10th power. However, we can think about this one by one, and we can say, well, this is going to be 0.5 times 0.5 times 0.5 times 0.5 times 0.5. Now, we could also ask a different question that's very similar. We could say, what is... don't know why that happened. Okay. That's interesting. All right. Try to erase that again, I suppose. Here, I'll just do that. We could ask, what is the probability of getting heads, tails, tails, heads, tails, heads, 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 tails, tails? All right, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's the probability of that? What is the probability of that specific outcome in that order? What do you think? Exactly. It's the same. It's the same. And the reason is we're dealing with a specific set of outcomes. We're not dealing with the count of heads. We're not dealing with the count of tails. We're not putting some other rule on this. We're saying this specific order, this specific outcome. And I think that's an important distinction to make. We don't need to construct a sample space in order to find the probability of this at all. We don't. We can just multiply, we can say 0.5 to the 10th power, and that's going to give us an answer. Now, there's another question we might try to answer. What is the probability of getting at least one head in 10 coin flips? What about that? What do you think about that? And maybe a good place to start would be saying, what is the probability of getting at least one heads in one coin flip? Okay, well, getting at least one heads in one coin flip is 0.5. And what about getting at least one heads in two coin flips? Heads, 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 tails, tails, heads, tails, tails. That's going to be 0.75, right? And what about getting at least one heads in 3 coin flips? It's going to be, I'll just start at tails, 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 heads, tails, heads, tails, tails, heads, 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 tails, tails, heads, tails, heads, 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 tails, heads, oops, heads, heads, heads. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8. Oh, I'm missing one. There should be another one in here. Heads, tails, tails, heads, tails, heads. Heads, heads, tails, heads, heads, heads. Well, I'm not seeing which one it is. There should be. Oh no, that's 8. I'm sorry. That's totally it. Well, the probability is going to be 7 out of 8, right? We can see that. All of those have at least one heads. So when we're thinking about this in terms of getting at least one heads in 10 coin flips, well, we've got heads, 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 oops, heads, 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 right? If that's not 10, it's 1, 2, wait, I'll just count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh my gosh, almost got it wrong. Okay. So that's all heads, but we're trying to think of at least one heads. Well, here's our next value if we're counting. Okay, there's a tails at the end. And we can keep going until we get all tails. It seems like 10 or 11, what it doesn't matter. Turns out that we can take the same idea, 2 to the 10th, and instead of it being 1 over 2 to the 10th, as we saw, one outcome out of 2 to the 10th, it's actually 1 minus 1 over 2 to the 10th. It's the complement. Complement's going to come back around a lot, actually, and so this would represent all tails, and then that's the only outcome where there isn't at least one heads, and so we can just get the complement of that, 1 minus 1 over 2 to the 10th. And then that saves us the trouble of building this huge sample space. So that is sort of this, that's going to be a recurring idea where we look at, let's say, the probability of some kind of event occurring, right? Some kind of event occurring. And in this case, let's say it's drawing a random number between 0 and 1. And we ask a question like, well, what is the probability of getting a value less than 0.25? Well, that's going to be 0.25. What is the value of getting what is the probability of getting a number greater than 0.25? It's going to be everything else, which is 0.75, right? 1 minus 0.25. Okay, so let's look ahead a little bit into statistical counting. Statistical counting is going to help us quite a bit in terms of the constructing of our sample spaces, how we think about probability in general. And there are 3 concepts that we're going to consider here. And they're heavily related to each other. Well, let's think about this as being 4 concepts. We've got counting as the concept that we've already started talking about. Then we've got factorial. And we can think about factorial as being a reduction. We reduce our sample space from counting to factorial. We reduce the sample space from factorial to permutations. And this is how we're going to approach it. There are different ways you can consider this as well. And then we're going to reduce the sample space from permutations to combinations. Okay? So these are the 4 concepts that we're going to explore in terms of statistical counting. We'll continue counting. That's just something that is going to come up a lot. It is really helpful. But let's start considering the concept of factorial specifically. So we talked about this idea with replacement. And we associated that directly with counting. Pretty directly, right? We said, okay, well, pull a cat out from the room, put it back. Oh, you can pull it out again. And then you pull out a ferret next, and then you pull out a goldfish. That, in essence, is going to give us the foundation to count in a base 4 system in that example. What happens if we're saying there are 4 animals in the room and we're going to pull them out and one by one, and we're not going to put them back when we pull them out. So we're going to say without replacement. And again, we've got a cat, a dog, a ferret, and a goldfish. Well, CDFG, CDGF, that's another way that we could do that. We could do CGDF and GCDF. And there's a lot more ways that we can do this, right? We can do GCFD. And you might notice that I'm kind of building a pattern here. I'm just saying G, F, C, D, F, G, C, D. This algorithm won't necessarily get me there in terms of building all the different ways to arrange these 4 items, but you get the idea. There is some systematic way we could probably do that, and we will explore that. But it turns out, let's try this with just 3 animals, because I think it'll be a little easier to see. Let's say we've got a cat, a dog, and a goldfish. Well, we can arrange them like that, and we can also say cat, goldfish, dog. We can also say, goldfish, cat, dog, goldfish, dog, cat. Let's see. So CC, let's do the D ones. We've got D, goldfish, cat, and D, catfish, goldfish, right? So that's 1, 2, 3, 4, 5, 6. Turns out that this is 3 times 2 times 1. Although the 1 is just identity anyway, so we don't need to worry about it too much. But this is 3 factorial. Factorial tells us the number of arrangements of n items. And when we say n items and number of arrangements, we're not leaving any items out. We are arranging all the items there. We're not going to leave any out. So it's not like we're going to say cat, goldfish, dog, and we're just going to select every way that we can choose 2 of those, right? Which would just be, or that we can, arrange 2 of them, which would be cat, goldfish, cat, dog, goldfish, dog, goldfish, cat. There's a few more of these, but you can see there are different ways that we might arrange these. Now, it's not leaving anything out. We're including all of them, and that is essentially, for us, the meaning. Oh my gosh, don't know what that's about. For us, that is the meaning of factorial. Oh, okay. Well, maybe that's a sign. Let's think about coding factorial. Now, I'm going to code factorial really quick, right here. And I'm going to talk through it. Factorial is one of those functions that of course, you need to be able to just code offhand. We would just expect you to be able to do that. And I'm going to just code this, and we'll do this again next time. So the factorial of some number is going to be that number times every value less than that number, right? Down to 1. Of course, we're not going to multiply by 0 because 0 would leave us with 0. Anything times 0 is 0. So, so for every number in the range starting at 1 going up to n, inclusive of n, we're going to multiply by that number, and we can return the product. So let's just test this. Print factorial of 5. So this should get us 120. 5 times 4 is 20, times 3 is 60, times 2 is 120. And it does. So how do we want to think about this in terms of, in some other terms, in terms of a story? So let's say we have 3 numbered balls in an urn. And in probability, we're always talking about, hey, you've got this bag and there's marbles in it, or you've got this urn that has, numbered balls in it, something like that. This is always the story we're telling. It's not sometimes it's not the most creative story, but it's nice to think about things in these terms because they're simple. And it turns out these simple rules, these simple constructions, lend themselves to a lot of much more complicated spaces. So on your first draw, you can either select ball 1, ball 2, or ball 3. If you select ball 1, then you can only select 2 or 3 on your next draw. And whatever your selection is going to dictate the third draw, right? So you can get 1, 2, 3, or 1, 3, 2 if you select 1 first. And then we can see it again, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. And we can see in this space, there's 1, 2, 3, 4, 5, 6 different arrangements of these 3 numbered balls. Turns out that we would call these, I like to call them arrangements personally, but more precisely, we call these permutations. So notice in a permutation, we care about the order of these items. We care what order we draw these things in, right? We're drawing 1, 2, 3, 1, 3, 2, 2, 1, 3. It matters. That matters. So, when we're calculating factorial, what we're calculating is the number of permutations of n objects. But what if we have a different kind of problem? What if we are thinking not in terms of the number of permutations of n objects? What if we're, oh my gosh, just trying to close that. What if we're thinking about the a subset of those objects, right? What if we're thinking about some subset of those objects? Like, see if I can just open my sketch program again that crashed. Hopefully it won't just crash again. That's interesting. Okay. So what if we have 10 objects, or let's say we have 10 people, okay? So we have 10 people. And by luck, they all have names that start with different letters. We've got Andrew, and we've got Barry, and we've got Carolyn, and we've got Daniel, right? We've got these names. And 1, 2, 3, 4, 5, 6, 7. Oh my gosh. And then I forgot the alphabet. Okay. H-I-J. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here are our 10 people. And we can think about, okay, well, we're going to select 3 of them to occupy, let's say they're running a race. I don't know, they're sprinting or something, and there can only be 3 winners, and there's going to be a first, a second, and a third place, right? How many different ways can we do that? The obvious place to start would be, well, maybe A, B, and C are going to be 1, 2, and 3. Then B, C, and D would be another possibility. Then C, D, and E. And then we can say A, B, and D, and A, B, and E, and A, B, and F. We can think about a systematic way to do this. There are a number of systematic ways to do this. But we're only going to take 3 of them out of the 10, right? So in this case, what we would say is that this is 10 permute, and this is how we would write it, 10 permute 3. So out of 10, we're going to take 3 of these, and we're asking the question: how many ways can we arrange 3 of these of any? How many different ways can we arrange any 3 of these 10 people? Right? That's not a factorial problem exactly anymore, but we can approach answering it with a formula for permutations. So n, 10 is n here, and 3 is k. Sometimes people refer to this as r, So n permute k is going to be related to the factorial. Oops, move that back up. But we need to reduce the space. There aren't as many ways to arrange a selection of 3 as there is all 10 of them. And so what we do is we say n factorial over n minus k factorial. And what this looks like, it's pretty easy to calculate this, actually. We can say this is 10 factorial over n minus k, which would be 10 minus 3, so over 7 factorial. And if we reduce this, because this is 10 times 9 times 8 times 7 times 6, this is 7 times 6 times 5 times 4 times, and so on, we can reduce this to 10 times 9 times 8. So what is that? 90 times 8, that's 720. There are 720 ways that we can permute 3 across 10. And so if we have a first, second, and third place, there are 720 ways. If we've got 10 runners, there are 720 different ways that 3 of those runners can place first, second, and third place. We'll do a lot more of this. We'll try to build out some intuition around this as well. Why is this a reduction? There's a systematic way that we can show that. We can go from counting to factorial, to permutations, to combinations, which we haven't talked about yet. But we can do that in a systematic, if somewhat not very optimal way using Python. We'll do that next time. Cool. So that's lecture for today. Stay on if you have any questions, and I'll go ahead and stop recording.